Let's take a look at the governing equations in the vector form, and then we will look at them in the expanded scalar form. In the vector form, conservation of mass, or the continuity equation, looks like that, and that's the same as what we had for the 2D Cartesian case, except that the velocity is now decomposed into a radial component and an axial component. And similarly, del, we have to use the cylindrical coordinates version of del. You can look that up in a textbook or for the younger generation on the internet. Conservation of momentum, F equal to ma, looks like that. So that's the same as what we had in the 2D Cartesian case. We have three unknown functions: the radial velocity, the axial velocity, and pressure. And each of these is a function of the radial coordinate and the axial coordinate. Okay, so we have three unknown functions, and we have three equations: one from conservation of mass, and two from conservation of momentum. F equal to ma in the radial direction and in the axial direction. The assumptions embedded in these equations are axisymmetric, because we have decomposed the velocity like that, and our velocity and pressure are a function of the radial and axial coordinate. Steady, incompressible, laminar, the usual suspects. We can also look at what these equations are when you expand them out in the expanded scalar form. And so here I've written that out. That's continuity. That's what the conservation of a mass for an infinitesimal fluid element looks like. And we can understand this, the physical principles embedded in that equation, by analogy with the 2D Cartesian case. In the 2D Cartesian case, I have du dx plus dv dy is equal to 0. And that term represents the volume change due to the shrinking or due to the shrinking or the expansion of the fluid element in the x direction, which means that that term must represent the change in volume due to the expansion or shrinking in the radial direction. Okay, similarly, that term must represent change in volume due to expansion or shrinking in the axial direction. That's what the momentum conservation, or F equal to ma, for the infinitesimal fluid element in the r direction looks like. And again, by analogy with the 2D Cartesian case, that must represent the acceleration in the r direction. And I know this must be in the r direction because I have derivatives of the radial velocity. That must be the net pressure force on the fluid element in the radial direction, and that must be the net viscous shear in the radial direction. And similarly, we have conservation F equal to ma in the axial direction, and we can understand each of these terms by analogy with the 2D case. And if you look at these equations, you're like, wow, it looks like it's a pretty complex set of equations, and it's nonlinear because of these terms. And so aren't we glad we have a tool that will help us solve it?